Let's look at proof by induction with series. The example says prove by induction that for all positive integers n, the sum from r equals 1 to n of minus 1 to the power of r times r squared equals to a half times minus 1 to the power of n times n plus 1. So step 1 is the base case, which is to prove the statement is true for n equals 1. So starting off with the left hand side and substituting n equals 1 in, we have the sum from r equals 1 to 1 of minus 1 to the power of r times r squared. Now this is effectively just the first term when we substitute r equals 1 into this expression. So if we do that, we end up with minus 1 to the power of 1 times 1 all squared. And so working this out, minus 1 to the power of 1 is minus 1, 1 squared is equal to 1, and minus 1 times 1 is equal to minus 1. Now doing the same thing on the right hand side, if we substitute n equals 1 into this expression, we end up with a half times minus 1 to the power of 1 times 1 plus 1. And so simplifying this, we end up with a half times minus 1 to the power of 1 is minus 1, 1 plus 1 is 2, and 2 times 1 is equal to 2. And so if we work this out, 2 times a half is equal to 1, and 1 times minus 1 is equal to minus 1. So since the left hand side equals to the right hand side, then the statement is true for n equals 1. Now step 2 is our assumption, which is to assume the statement is true for n equals k, where k is some positive integer. So in other words, all we've done is replaced n with k, and now we're assuming that this is true. Step 3 is the induction, which is to show the statement is true for n equals k plus 1, where k is some positive integer, using the assumption in step 2. So we start by writing the statement out again. So we have the sum from r equals 1 to k plus 1 now of minus 1 to the power of r times r squared equals to, and now we're trying to show that this would equal to a half times minus 1 to the power of k plus 1 times k plus 1 in brackets times k plus 1 plus 1, if we were to replace n with k plus 1. So if this is what we're trying to show, we'll start with the left hand side. So we have the sum from r equals 1 to k plus 1 of minus 1 to the power of r times r squared. Now this is equal to the sum from r equals 1 to k of minus 1 to the power of r times r squared. And now the final term in this summation that's missing is k plus 1, because this is the terms from r equals 1 all the way to k, and now we just need to substitute k plus 1 into this expression. So we add on minus 1 to the power of k plus 1 times k plus 1 all squared. And the reason this is helpful is because we can now see that this series is our assumption, which we can replace with the right hand side here, since we're assuming that this is a true statement. So we now have half times minus 1 to the power of k times k plus 1, and then we have plus minus 1 to the power of k plus 1 times k plus 1 all squared. Now we can see what we are trying to show has a half factorized out and a k plus 1 factorized out. And from these two terms, they both have k plus 1 in common, and we can also factorize a half out. If we do that, by factorizing a half, we end up with a half, and then factorizing k plus 1 in brackets. In square brackets, we then have that for this first term, we're left with minus 1 to the power of k multiplied by k. And then for the second term, we're left with 2, because 2 times a half is equal to 1. And then we have times minus 1 to the power of k plus 1. And then we have a single bracket for k plus 1. Now we can see that in the final answer, we have minus 1 to the power of k plus 1 factorized out. And if we focus on this first term, now minus 1 to the power of k can be written as minus 1 to the power of k plus 1. And now using index laws, we have times minus 1 to the power of minus 1. Because the bases are the same, if we multiply this, we add the powers. K plus 1 plus minus 1 would just give us k. This simplifies to minus 1 to the power of k plus 1 times minus 1. So if we replace minus 1 to the power of k by this, and we also factorize the minus 1 to the power of k plus 1 out, we would just be left with a negative 1 on the inside. So doing that, we end up with a half, and then factorizing minus 1 to the power of k plus 1 out, we have times minus 1 to the power of k plus 1 times this bracket, k plus 1. Now in squared brackets, like we said before, factorizing the minus 1 to the power of k plus 1 out from this term leaves us with minus 1. So we get minus 1 times k, which is minus k. And then since we factorized minus 1 to the power of k plus 1, we're left with 2 times k plus 1. And we're adding that on. If we further simplify this, we end up with a half times minus 1 to the power of k plus 1 times k plus 1. And then in the square brackets, we now have minus k. Now expanding the bracket, 2 times k is 2k, and then 2 times 1 is 2. And so if we simplify this, we end up with a half times minus 1 to the power of k plus 1 times k plus 1 times in squared brackets. So minus k plus 2k is k, and then we have plus 2 on the end. And so if we want to rewrite this in the format that we're trying to show on the right hand side, we know that 2 can be split into 1 plus 1. So therefore we have a half times minus 1 to the power of k plus 1 times k plus 1. And then for the squared brackets, we can now write k plus 1 plus 1. This is what we're trying to show on the right hand side. Therefore, this statement is true for when n equals k plus 1. So the final step in our proof by induction is the conclusion. And so we have that the statement is true for n equals 1, which we showed in the base case. If the statement is true for n equals k, so provided that our assumption is true, then it is true for n equals k plus 1, since we've shown that through our induction. And so therefore the statement is true for all positive integers n. That is our proof by induction for this question.